this is just RAM. So this multi-line, this is the address you want to pull from. Actually, I think I can condense this to one line, since I'm not doing such a big address last time. Yeah, I think I can do that. So this is going to be probably a single line instruction. Branching is going to have to be 2 lines though. But yeah, so I've got a 6-bit address, 64 bytes, and this is whether to read or write to it. Then this address is whether it's like, actually I need to add another bit to it. So whether it's loading or storing, and whether I'm using a pointer. So yeah, so this is the, say if I want to load register 5, I'd say I don't want to use a pointer, but I want to store that. Then I do address, I don't know, that. So that's how that works. The pointer is basically a number, like a word in memory. So say if I wanted to use in register 5, there was 5, and I wanted to use that pointer. So if I do 5, that'll load a 5 into the address of the RAM, and that's how you can do stuff like linked lists and stuff like that. So let's go down. This one, I think I'm gonna use that as a peak. Oh yeah, I forgot to add, I've got some stuff memory mapped. I think some serial stuff, stack, bar shifter, and an offset thing for the PC. And yeah, I think I'm gonna add peak though, so I don't know just yet. Peak is basically on the stack. Instead of pushing or popping, like popping, instead of popping, you just read the top without actually popping any data out. So yeah, so next is external hardware, self-explanatory, any hardware you want. I like HGXU. External hardware. Anyway, external hardware, just basically you load 2 things to any hardware you want, and this is the address for the hardware. I do have what's it called? There's a special word, interrupts. I do have interrupts in the CPU, so they can't really talk. Really, it's more like a one-sided thing. Call on a CPU, PC even. If you call for an address for the PC, it's basically, it gets stored into a stack or like a register or something, and then when you return, it takes that thing from the stack or the register and puts it into the place where it wants to jump to. So here I've got, if you want to call to the stack or the PC register, then PC register address, I've got 2 bytes, 0 and 1, and I can either load an immediate or a pointer to the register or stack. So, and you can see that I don't have return here. Since I didn't want to make it multi-line, I put the return down here. I think it's, yeah, it's here. So yeah, going on to the branch, this is the return if I'm going to do that, and that's the that's basically this over here, except to return. And then here, oh yeah, so these 2 addresses are to compare, which is subtraction, and then you save the what's it called, the flags. For example, the only 2 flags I'm really gonna have is carry out and if 0. With those you can do greater than, less than, greater than, equal, and stuff like that, and pretty much all 4 of them, in addition with if 0 and carry out. Yeah, so this selects which one you want, which condition you want. This is whether you want to branch to a pointer or immediate. And yeah, that's pretty much for the IS. Another thing is that this is pipelined. Basically, as one instruction is getting goes in, when it's at the next stage of getting executed, another one comes in. So basically, I don't know a good analogy. Basically, when you're washing dishes, you're not gonna wash one dish and then have to wait for another one to soak for a few minutes. Because if you're washing really greasy pans, you're not gonna bring one pan, put it into the sink, then wash it, and while the other ones stay at the side when they could be soaking at the same time. So in pipelining, you take the pan, while you're washing one of them, you put another one into the water to soak. Then when you've finished that, you put that to dry, and then you keep doing that cycle, but without any stopping, really. So it's just a little bit quicker like that. So this shows it off. So I'm not really good at explaining, but I'll try my best. So I've got load immediate here, compare and branch. As you can see in the multi-line thing, compare was at the top and the actual branch was at the bottom. So this is how it looks to the at the CPU. Like this is what the opcode actually looks like to the CPU. So it's in 2 separate things. Compare, branch, add, external hardware, compare and branch again. So this is just a test program. So the load immediate comes in. It gets fetched from the prom. Then while that's getting decoded, I've already forgot. The compare is happening. The compare gets fetched, and when the load immediate gets executed, e.g. getting loaded from getting stored into the register, the compare is getting decoded in decoder 1. That's that thing. And then while that's happening, this is getting fetched from prom. So that's basically after on the 3rd instruction. This is basically if I did a program without any branches, or basically I think it's only branching that actually makes a bubble. This is like 3 things happening at once. So basically, since this is a 14-tick data loop, I can do a 14-tick pipeline. And the reason I did 14-tick and not any faster is because I don't want to add stages in this one. I wanted to make it simple. So basically, the register is a stage, if you get what I mean, or any of the places to save stuff. So like the stack, the registers, the history table, So okay. So yeah, the reason why branching is, this is a branch. The reason why there's a bubble in branching, actually this would usually be like this, so I'm gonna have it like that. The reason there's a bubble in branching is because since you're gonna be branching and you're gonna be doing some other ops, you do not want it to interrupt anything that's happening to this. So say if you I think I may have it so that any mod 1 stuff updates the flag register thing. So basically, if there's an op that stores a anything to the flag register, the branching will get corrupted basically. So say if you did loaded immediate 1 and there wasn't a carryout, and then you did add, then there was like a carryout there, that caret would say that basically this branch was true or something like that, and then you'd branch to elsewhere instead of that the real place that you needed it. So basically by doing this is a bad example because I just told you that mode 1 will update the thingy, but you can do a one extra op between the inside the bubble to reduce the actual time that it's wasting. So yeah, this is RAM access. If you did, it's not there, but yeah. So that's by smart programming you can do an op that doesn't actually affect the branch. So the bubble is here. So basically in 14 ticks this was finished, 14 ticks after this was finished, 14 ticks after that was finished, and 14 ticks after that was finished. So this will have to wait 28 ticks till this is actually done. So this is way quicker than normal single cycle CPUs, because it'd be more like this. So say if this was the whole instruction there, it would be like this. It'd have to do the full thing before it can actually start again. So then this would be the next instruction, and then this would be the next instruction. By the way, the bubbles are if no ops. It's the same as the bubble, it's not doing anything. It's like this, and since they're not doing pipelining, this won't even matter, the bubble part, so that's the only way that's getting covered up, but it's getting substituted for bigger bubbles. But anyway, so all these bubbles, just nothing happening, is a single cycle CPU. So if this is a 12 tick what's it called, 14 tick pipeline, so say if every thingy was 14 ticks, so every stage was 14 ticks, that would be I think 42. So 42 ticks for this whole thing to complete, then another 42, then another 42, then another 42, and yeah, this is hella slow. Instead of the thing being done every 14 ticks, if you get like a perfect program which doesn't need a heavy amount of branching, yeah, in fact if you get a program that doesn't need branching, I would be surprised, very surprised.